to our colloquium, and she'll talk, give the co-public lecture tomorrow at 4:30. There's a reception in the atrium at 4 o'clock. And I have a whole page of accolades here, and Seth warned me not to take too long, so I'll just show it to you. So Ingrid Daubechies got her oh no, I'm not serious. You don't understand that easily. Got her degree from the Free University in Brussels, and actually began her career in physics. I went on to work at Bell Labs for 6 years or so, until the early 90s, and took a job in Princeton, rising to professor. And let me see, I've got a lot of things I wanted to read here. So in 1992, she published her famous book, 10 Lectures on Wavelets, and that led to the AMS Steele Prize in 1994. She was a MacArthur Fellow from 92 to 97, that's the Genius Award, and she was in the mathematics department at Princeton from 94 to 2011 before moving to Duke as James B. Duke Professor of Mathematics and Professor in Electrical and Computer Engineering. She's had many honors and awards, and this is a very small selection, but she's been elected Fellow of all sorts of academies, so I'll just read you a short list. The American Academy of Arts and Sciences in 93, the National Academy of Sciences in 98, the National Academy of Engineering, the Royal Netherlands Academy of Arts and Sciences. She was president of the International Mathematical Union from 2011 to 2014. And then she's got a lot of honorary degrees. I counted 6, maybe there are more by now, I don't know. But from Oxford, from the University of Pierre and Marie Curie in Paris, from Genoa, and there are 2 honorary degrees from Belgium, and then from Lausanne, Switzerland. So it struck me that that's quite a tour of Europe. That's very impressive. She's given many distinguished lectures, including the Kovalevskaya lecture, Siam lecture, and the von Neumann lecture. And recent successes include a very large Simons Foundation grant, which involves collaboration with electrical engineering on training computers to find patterns in massive data sets from medicine to art history. The lecture today is Machine Learning, Fibre Bundles, and Biological Morphology. Thank you.
It's a pleasure to be here, and I confess I wrote the title with a little bit mischievously, because it combines 3 things that you might not expect to find together. And I hope to convince you that, at least in some projects, they do belong together, naturally. So, page down maybe. I refused the clicker, saying that I would just leave the screen, but the screen is not doing it.
Would you like the clicker, or would you like the...
I would like anything that will happen.
The arrows don't work?
No, page down doesn't work, arrows doesn't work.
It's a new version of the Adobe.
So the clicker does work. Okay, so we'll talk about geometry of shape spaces, and there's a whole range of collaborators, and in fact they're not even all on there, but let me just mention in what fields they are. Yaron Lippmann and Roy Boran are in computer graphics. Rabravir and Damon Yao are in mathematics. Jesus was in mathematics but left for Wall Street. Lima is at ETH now and in mathematics. Daubechies, on the other hand, is a biologist in the Department of Evolutionary Anthropology at Duke. We started working before either of us had any idea we would end up at Duke, so it's really very convenient that we're now the same place. So it all started really about, almost 10 years ago with a conversation I had with Ingrid, who I met serendipitously at a party where there were scientists of all kinds of stripes. And he is a biologist, but more precisely a biological morphologist, which means that he studies especially teeth and bones of both extinct and still existing animals. Daubechies was then his postdoc and is now, as I said, assistant professor at Duke. And it really started in which, in a project, Jukka Jörnval at this party explained to me something he worked on, which he said, oh, you're a mathematician. And, so recently he had published a paper in Nature of which he was very proud, which looked at the complexity of the chewing surface of molars in mammals. And I said, so how do you measure the complexity of so what he had shown, and which was what it was published in Nature, was that the complexity, from the complexity he could very reliably infer whether these animals were insectivore or frugivore or mostly vegetable matter or carnivore and so on. And it was so systematic and so reliable, regardless of the scale of the animal, mice to elephants, that it then could, and that's what biologists always like, when they have something reliable, then they can extrapolate it and then they can use it as a tool to assert things about animals, extinct animals, for which they don't know stuff about animals. I said, well, how do you measure complexity of teeth? And so I was really surprised because he told me, oh, it's very clever. I mean, we look at these surfaces under a computer graphics tool. That's a kind of standard tool that illuminates it with red and blue and white. And we take a snapshot from above, and so we have all these little triangles. And then we count the transitions from red to blue to red. And I said, but what you're looking at is a change in the direction of the normal. I mean, you're integrating some kind of curvature. I said, we have better ways of doing that than looking at this color. He says, really? And so that's how the collaboration first started. So in a sense, it wasn't kind of off-the-shelf mathematical idea that we used. It turned out it worked very well. I mean, Yaron Lipman, who was my postdoc and who's a computer graphics guy, and we'll come back to what computer graphics, what role it plays in all this, built a program that gave a much more reliable way of computing it. They called it the Dirichlet normal energy, DNE. So DNE now, in every one of these morphological conferences, there's now a special section on DNE results and so on. So that was the first, but then of course, and as often happens in my collaborations with people in other disciplines, a first easy thing leads to much better, much deeper, much more interesting problems, much more interesting conversations. So then soon after we started to try to find ways of computing precocious distances between surfaces without landmarks. So let me first tell you what all this means. So in order to compare, let's say, teeth of different species, closely related species and so on, and to extract from that quantized data that then can be used for a statistical test and so on, what morphologists have been doing for generations is, because of their domain knowledge, they know what are special points, which they call landmarks on these teeth, that they mark. And it used to be that they marked them with very precise color, paint, and then measure distances with some apparatuses, and now of course all that works digitally, but they still mark them manually, albeit digitally on their screens. And they then, they know also what the correspondence is of these things. So for every landmark xj here, you know what the yj is. You then look at these pairs, you move this tooth so that it is in the closest possible bi-rigid transformation correspondence, and you look at the sum of the squares of all these distances. And you define that as the progressive distance between these two surfaces. And now, what they were interested in doing is to find a distance that that gives you as good results for biological purposes as the progressive distance based on these landmarks placed by experts. The reasons for that were several. One of them, probably not the least, is that it's kind of time-consuming to place these landmarks. And so the mind boggles. I mean, of course, what happens is that undergraduates get trained to do this, and I mean, it's still not a very exciting pastime, but typically collections, just enough is done that you have statistical strength to your sample. I mean, you don't, if you could, biologists, I mean, if you talk about bones, they have drawers full, and teeth especially. Teeth are the hardest bone, so they have zillions more teeth than they ever want to landmark. And so if you had not enough of that would be great, because you would just be able to do much more. Okay, so these things are very finely discretized. The way Doug actually was the pioneer in a new method of landmark, of getting these very nicely and very finely digitized. What he does is he actually, wherever he goes in the world, he visits the local museum and makes casts with dental resin of their teeth. Even some of them are very precious specimens and are not allowed to travel, but typically they will allow an expert to make a cast. And so he has these casts, which then are uniform in structure, so you have lost, of course, the internal structure of the tooth, which for some things is a drawback. But for what he wants to do, which is extract that surface, it's a positive, because he then takes the casts and he micro-CT scans them, and since they're now homogeneous, the extraction of the surface is easy. So he has these beautiful surfaces. Now there is a whole lot of work that goes into that as well, but let me speak that under the record. So when I first learned of these things, I said, you know, I am going to have this postdoc with who I work on mathematical problems in computer graphics. But that's exactly the kind of thing that he might have skills for. So let me tell you why I would expect a computer graphics person to work. Because there are problems in computer graphics that actually closely resemble what we have here. Okay, what do computer graphics do? Computer graphics work with surfaces and so on, and the whole growth of the field was driven by animation, first for movies, and then now increasingly by video games. And in fact, computer graphics, after shrinking a little bit as animation for movies became standard, is now growing again as video games are growing more and more. Okay, so they rely on three-dimensional mesh models for surfaces. The very first one of those realistic surfaces was the teapot. The teapot, this is a model that was done in the 70s somewhere, maybe the 80s, was because instead of these artificial things, donuts and things with handles and so on, the spouse of computer graphics expert said, why don't you ever use an object then? Was holding up a Melita teapot. And so this became the teapot. This was discretized. You have now a much more fancier version, and it's actually an in-joke. In every Pixar movie, there's a teapot somewhere. Me, with my kids, we would try to hunt for it. They became, of course, much more complex over the years. Here are some, these are already 6 or 7 years old, but fanciful architecture or a real object. This is actually an object that is manufactured. Of course, since then we are 3D printing and much more. Also, the way the surfaces were represented changed over the years. These are two figures of Pixar. This is a figure in Toy Story 1. This is the toy doctor in Toy Story 2. The way surfaces were represented in Pixar changed between here. They are piecewise splines, box splines, so nerve surfaces. There they are subdivision surfaces. Subdivision surfaces enable you to do much more complex things, like creases of nails and so on. The whole hand of that person is just one surface. While in animating not Woody but Buzz Lightyear, they actually had to put a special crease because it made the animation easier because of the whole nerve construction. Anyway, we are interested for this biology in existing objects, and those can be scanned by different technologies, and what you end up with then is a whole point cloud. In the case of Daubechies, it's not none of these two methods. It's this micro-CT scan. But in any case, he gets a point cloud too, and you triangulate that, and you can then use that. I mean, here you have a virtual representation of a real object, and then the same object. In this case, it was milled because that was for this detail. Then still cheaper than 3D printing it. Once you have these surfaces, you can edit them, and that's why people use them in computer graphics. You have a whole hierarchical representation, and then at a low level of the hierarchy, you can do something, and all of a sudden your camel starts talking. But when we talk about real objects, we have different challenges. Different challenges, namely, if you scan the same object twice, you get a completely different point cloud, a different triangulation. How are you going to recognize that it's the same object? I mean, you need to be able to see that. Or, if they're not the same object, that they're close to each other. I mean, how are you going to quantize that? Or, in this case, I'm comparing a Volkswagen Beetle and a little dinky toy version. Now, if you scale the Volkswagen, the dinky toy actually is much more stubbier than the scaled Volkswagen. When they first designed these dinky toys, they found that if they just scaled down the Volkswagen, it didn't look right from that scale. But how would you know that if you had point clouds for both of them? So you need ways of comparing, of finding distances between surfaces, just like the biologist does. And there are applications even where you use landmarks. I mean, here, for a lot of animation, and animation of humanoid figures especially, typically an actor is marked in crucial points with sensors and goes through the motion. The coordinates of all these sensors are registered and are then used to animate that humanoid character. So landmarks, the reason for that is that as the character moves, of course, these are surfaces that are very much related, but the corresponding landmarks help you in doing that animation. So people in computer graphics are interested in putting landmarks automatically if surfaces are very closely related, because it can help. Now, the movie industry can afford to put actors and sensors, but for biological experiments on locomotion of lemurs, for instance, that they do at the Lemur Center, they would love to have a method like that, rather than having to shave little pieces of fur and put sensors on the lemurs, which they don't like and they probably might not move as much. Okay, so these are the things that I have said we would like to be able to do. And correspondence points on similar surfaces is exactly a problem that I knew Yaron was interested in working on. And in fact, the very first work we did, we used stuff that we had published in SIGGRAPH and transplanted it to this biology. But what we then ended up with in the end, so what we did is we defined distances between surfaces that were very much governed. There exist already billions of distances between surfaces that are well computed and so on. And the one that, when we started, that everybody was buzzing about was the Gromov-Hausdorff distance, which is also a beautiful construct and has turned out to be useful, but it's very heavy to compute, and it turned out for the applications in which Doug and Yuka Yongo were interested, not to give good results. So we very much, and the whole collaboration, even now, we are continuously working closely with the biologists. We need not just to talk about results, but also talking about the frameworks and so on. And we found that actually very useful in trying to explain some of the mathematical framework and what it translates to in their words. Okay, but so what we ended up with was we had two ways of defining distance. One which uses uniformization and then looks at the conformal factor as a distribution that you might want to transport. So we call it the conformal Wasserstein neighborhood distance. We had to have conformal invariance also, so that made it different from standard transport. The other is one in which we define a continuous procrustes distance. So, and we try to find an analog for the procrustes distance with landmarks, but in a situation without landmarks. And what we then, to compare the two, we looked at what distances that the biologists determined based. So observer determined landmark-placed distances. I mean, they chose the acronym. And our conformal Wasserstein distance, neighborhood distance, or continuous procrustes. And we labeled the 100 and something samples so that things that were more similar had labels close to each other. And for reasons I'll come back to, we were especially interested in getting the small distances right, because large distances we don't trust so much in, and we'll have a different solution to what do you do then when things are very dissimilar. But so we're looking here at two zones, and based on this, we actually are now much more using the continuous procrustes distance, even though I had a soft spot for the conformal Wasserstein neighborhood. I really like that, but the continuous procrustes came out better. But you see how well it reflects the local structure. So the lower triangle is theirs, the upper triangle is ours. Now, here we actually compare. This was a way of comparing by comparing the matrices. Here we compare by looking at landmark transportation. So on three different kinds of bones, here you have molars, here you have a metatarsal bone, and here you have the end of one of the leg bones, the radius. Here a comparison between a non-primate and a primate, here a monkey and a lemur, and here a human and an ape. On both of these, we actually asked the experts to put the landmarks. This continuous procrustes distance actually defines a mapping from one surface to the other. And so we would, through our mathematical mapping, transport and then compare with their placements. And so that was a way, even though our method was not placement landmark bound, was a way of comparing in their terms and for their assessment. And we were surprised at how well the method did already. Not only did it well, but then if you, it even, and this is something that Doug put in, at the time when this paper was published, it's a paper in PNAS 5 years ago, there had been a recent controversy between the comparison of these two teeth, where this entoconid was placed by an expert here, but where it was felt that by others that it really should be put there. And what we did is we used our way of defining this mapping on this pair straight away, or, and that's exactly what the biologists had also done in order to resolve this question, on paths that made smaller hops, either through an extinct common ancestor, or two still extant animals, but where the relationship between every two was much closer than between these two. And both of these showed that it was more natural to map to this other location. And our algorithm did exactly the same. So he felt that this continuous progressive mapping was really capturing something that the biologists were doing as well. Okay, but something interesting happened. I mean, so we were there and we could do more with it, but our maps were still not perfect. And what happened actually is that we stagnated for about a year. We had discussions and so on, and we needed more data, but they were not giving us more data. And it occurred to me, suddenly it came to me. What in fact was happening was that as they saw what techniques we were using and what methods we were building in order to get to our results, their wish list was changing. Although they had asked us from the start to build distances that were similar to their progressive distance. And we were doing something that was doing a pretty good job at that. In order to get there, we were making these mappings. And they were then starting to reason much more on the mappings. So even if the distance was good, but the mapping had a defect that they didn't like, then they didn't want to go forward. So it then became clear that the mappings were really much more important to them than these distances. They had earlier never seen it in terms of mappings, because they put landmarks, and so their domain knowledge put the mapping, the marks. And then they were trying to do things in distances. But now that they saw that we really had a mapping of the whole surface, they liked that, and they wanted those to be good before we went. So we then started talking about the mappings. And yes, I mean, the thing is, they don't come to you and they say, oh, you build mappings and these mappings here. I mean, there was reluctance and so on, and you have to distill this out of it. And that's why it's so important to have regular meetings. I mean, to kind of articulate what is going on. And so, yes, the mappings were important. And they said, because they also expect in our terms, that these mappings would have trivial homonymy. Because they expect the mappings, really, that you have a mapping if you have a common ancestor, then they expect that both if you look at the second lower jaw, left molar or something like that, and you map it to the corresponding tooth in the ancestor, you expect that both get mapped here. And the right correspondence is the one that would do that. So if you then have a third one, the right correspondence would also go through, which means that the correspondence among the three of them should be completely consistent. You should have no homonymy. If you do a tree cycle, you should come back to the same place. Now that was something that makes sense in the mappings that we hadn't thought of in terms of the distances. So that led us to think of the whole problem differently. And in fact, Tingran Gao, who was then my graduate student, who's now a postdoc, reformulated the problem completely as a fiber bundle. I mean, what they really are telling us is that each tooth is really a fiber. It stands for an individual. These individuals lie on a manifold. You might say, why a manifold and not a tree? Well, because there's enough variation that things overlap and you have some continuity. Okay, and so what you do is you have to find a mapping on that fiber bundle, which is a connection, and he then did a different type of analysis on these data. Okay, now in order to show to you, so that was the very first result, that in fact, so we then started looking, as the biologists implicitly do too, at the whole collection rather than pairs. They implicitly do this too, even if when they put these landmarks, typically they look at something like 15 or 20 or so. They can do it with 2 as well, but usually they want to study something, so they look at more. But what they have is a whole domain knowledge, and which is very important, because in this whole landmarking process, Doug told me he only trusts a graduate student to be really consistent in that after a while. Or undergrads that they're trained in this. It takes them a whole lot of seeing these things before they can be trustworthy in put in that landmark. So you have a whole lot of domain knowledge, and that comes from seeing collections. So here are these 4 teeth, and what we, in order to, with the continuous processes maps, to get an idea of whether the collection would give us more than each individual, what Ingrid made the following computation. He said, let's take these 4 surfaces, and let's make an enormous matrix. So we look at a data set as the union of the 4 surfaces. And we have an enormous matrix where we put between every 2 of the surface of every pair the correspondence map. So we put them all together. If there truly is a real correspondence, then you would expect that the vector that has the same points, the corresponding points in surfaces 1, 2, 3, and so on, gets indeed always brought back to the same place by that matrix, and so it would become an eigenvector. So you would expect this thing to have many eigenvectors that are 1 or very close to 1. In practice, of course, your correspondences are not exact, but you'd like there to still be some trace of them. Then they're not exact, so we won't look at M on a vector giving the vector itself again, but we like vectors that are close to being left invariant. And then we also wondered whether you could find, because if it were truly correct, we would have an enormous eigenspace of vectors. So we were trying to see, can we find the points then? So we say, let's make these vectors very sparse. So we wanted sparse vectors that were going to be close to eigenvectors with eigenvalue 1, and to make them sparse, if you have something that has a sum of squares equal to 1, make sparse means very peaked, so that means the L1 norm close to as large as possible, as small as possible, sorry. Because many small ones will, if you take their square root, give you a bigger sum than if you just have 1 thing. Okay, so we minimize that functional under this constraint, and what you find is indeed, without having imposed that these vectors consist of just 4 entries corresponding to the 4 different surfaces, you find indeed that you find locations that correspond well. So that gave us an idea, the first evidence that indeed the collection of all the maps, by combining them, we could denoise them, because for 1 pair it wouldn't have given us. Okay, so that's what we're going to do. So here, let me tell you about the continuous progressive distance. So in the progressive distance, what I was doing is I was labeling points on one surface xj, and on another surface yj. And then I was finding the best r to put these things, and I was looking at the xj minus yj distances. So when we work with the surfaces continuously, meaning much more finely discretized than the 20 landmarks, what we do is we find first the correspondence x to y. Because when they're landmarked, they have their correspondence x1 to y1, x2 to y2. So we take a c of x. And then we take the axes and try to rigid motion them and look at x and c of x to be as close together as possible. So we minimize over a class. When our teeth are fairly similar, we we defined it mathematically, and we proved properties about that mathematical distance with the class of area preserving surfaces, which certainly is not right if you go look at things that are very different. It's also not very good to search over, even when things are very similar. But what we could prove was that if things are not too far apart, then if they are, if there's an area preserving, if the minimizing area preserving is close to, is not very far from one that is almost conformal, and so we search the conformal distance, the conformal maps. These days we look at quasi-conformals and we minimize conformal distortion. In any case, so that's how we defined it. And the thing is that from this definition, you see, you have a mapping. The thing itself comes with a mapping. So you have to minimize here over the rigid thing. It's easy to minimize over. It's a trivial computation. It's just a single value decomposition. But then you can minimize over C. But once you've done it, you have your C. So that's how we had our mappings. Okay, distances. So now we've talked about the morphology. We've talked about, what did I also say? Machine learning. Fibre, we've talked about fibre bundles. Now we'll get a little bit into machine learning. When I have all these distances between these surfaces, you can try to make the best possible projection of that matrix into a 3x3 matrix that preserves the geometric structure as best possible. Of course, you can't do that exactly, but you can find the one that is best, and then you can map that. And you see things, same color dots, same species, do cluster somewhat. This is the continuous progressive distance. So you have a complete graph, in this case, in 6 things, and I have all these distances. Once you think of it in terms of machine learning, you can also look at something that's called the diffusion distance. And you see here that once we look at diffusion distance, we do better. So let me tell you a little bit about diffusion distance.
What are the 3 axes in this plot? When you make a projection?
They're just from this, in this particular 6-dimensional space, the 3 axes on which use the geometry is best preserved. That's all you do. So you project on a 3-dimensional space. You have then the actual distances, and you want that matrix to be as close as possible to the original matrix. Okay. So how do diffusion distances and diffusion maps work? The idea is, if you have a whole manifold living in a much higher dimensional space, you typically don't know your manifold. You are hoping that you have a way of computing distances in this high dimensional space, so that for things that lie very close to each other, you're close to, if you think of it as something in a big Euclidean space, you're close to the Euclidean distance, and that is close to the distance, projection of that distance on the tangential plane. And so it's close to the geodesic distance. But that's only for things that are very close to each other. It's not for things that lie far from each other. I measured this distance and it would be. But what you can say is, you can, and this is my way of I imagine this as a bubbly thing with little doilies. I put little doilies all over, and the little doilies nicely conform, and that gives me a way of measuring distances. I have a lot of craft analogies. My students they counteract all these sports analogies. So I have neighborhoods on which I trust the distances. So I trust these little, tiny little distance networks I have then because they are overlapping points, I can knit it together. And so I get a much better idea from the distance of very points that are far from each other by linking them over this little thing. So what that means is, in practice, what I do is I take my distances, the ones that I measure. I build from that a random walk. So I like to think of it as I'm building e to the minus t Laplace, and with t not too large, so that I really hop only little bits in my random walk. But then I can look at powers of that matrix, and that is hopping many times and giving me big connections. So in practice, what you do is you try to look at the spectrum of that. So you represent each point, you look at its coordinates in the low eigenvalue vectors. So this gives you an n-dimensional representation. And you can play with t, and often it's useful to look at a variety of t. In principle, the limit for t going to 0 is what gives you the Laplacian. Okay, so you can then, by using these eigenvectors, look at a distance that's defined by these eigenvectors, by this random walk, by this, and that is what people call the diffusion distance. And that's by doing this scaling, this best three-dimensional projection with the same distance, but after having computed the diffusion distance from it, is what I get here. So things are much clustered, much better. So this is already using the whole collection, because I'm using all these little distances to make that big matrix. So you already do some, what people call denoising of the true concept. So that's, but what Tingrans did for his thesis, actually, he realized that we had more information that we could use than just the diffusion distance built from the continuous process distance. And he built a horizontal diffusion distance, base diffusion distance, that actually gives you even better clustering. So how did we get to that? Well, again, we're going to use the information that lies in these maps. We have the maps. So, in fact, so the maps give us, at first instance, you might think you have the triangles on one surface, triangles on the other surface. We just map vertices to vertices. Well, you can do a little bit better than that. Because what happens is that the best correspondence might come when you, in fact, there's no reason, because the triangulations were just coming from your data analysis, why that point should end up at a vertex. It probably will be somewhere in the middle. So it will be, if you then replace it by its barycentric coordinates within that triangle, you have these numbers here, and so you can build a little diffusion matrix based on those distances. And so what it does, I mean, what we're doing now is we're replacing this one number we had between surfaces with something that actually gives us, depending on the diffusion parameter, which we can tune, something that looks at the whole mappings between the two. And you can then, just like you had a random walk before, on the base points of the manifold, we can now try to use the whole mapping in order to do so instead of looking just at these, we are going to use the fibers completely. And fibers correspond to mappings. And here we've just done one horizontal slice, but there exist many, all these different slices. And so instead of building a diffusion map the way machine learning techniques, standard machine learning techniques have done it, like looking at this matrix at the ith and the jth row, we're going to make a much bigger matrix where each of these is replaced by each of these entries is replaced by a little matrix that encodes the map. And that has actually another parameter that we can do. And that means that your vectors, of course, are going to be much bigger vectors. And we can then, instead of having every entry here, which would have been a red, a yellow, or a blue, or and so on, every one becomes a vector, and we make this enormous vector. And in a sense, that's what we were doing here already, but not as precisely. So you can then build the eigenvectors, and so every surface is then represented by a matrix that looks at how many of the eigenvalues I look at, and the whole structure on every surface. And you can do diffusion. So that's the difference between what we did earlier and now. And you can use that then to, okay, you can use it for a number of things. First of all, since you're trying to bring them all together to this mapping, this consistent mapping, you can use that to do a global registration, meaning you have one template and you can register them all together. And so if you have a point on one, you can put that on the joint template and bring it to the other. So this is the more fancier form of that earlier trying to find these correspondences. This was actually something that is also used in computer graphics. And when you use it in computer graphics on all these different objects, what you find is that, for instance, this is a SIGGRAPH, 2012 SIGGRAPH paper, that all these different things come out as similar. So you can also do some clustering. So what's done here is that the regions on the template points are chosen that are far apart, and then kind of Voronoi regions among them. And that is then mapped to all these teeth. Now, we thought this was just a nice illustration of the whole thing. But Daubechies was really taken with this. And then a student, he just was telling me the other day, I was telling him, hold your horses, we're not there yet, we want to do more. He says, I want to do things. So he actually had a student look at this segmentation of these different zones and look at whether they were correlated, their area or their change of normal was correlated to things that were biologically significant. And he indeed found that he could do things with this biologically that he was very excited about. So now they want to validate that. So again, to have a tool to use. Now, I think this will not be the ultimate thing. I mean, we want to be able to get better at it. But it's already surprising to me that this was going to be useful biologically to do as a tool that we hope to hone. You can also, once you have these diffusion maps, you can, from these vectors, try to build, again, a lower dimensional matrix between the different points. And you can have a lower dimensional by just taking inner products of the vectors corresponding to different surfaces. And you can then look at that and build a diffusion distance on that. And that was the distance that gave him this much better graph. So this was, we wanted to do this to see whether indeed, because the earlier thing with the segmentation had not been done yet, that's much more recent. This was about 2 years ago. We wanted to see whether we were capturing more biology. And when the clustering came out so much more nicely, Doug was very excited. He says, let me see what the labels are, because maybe this becomes a phenotypical tree, etc. But why would we get that from one tooth? Come on. And indeed, so here are the different, for those of you who know their lemurs well, you immediately recognize the different lemur species. These are the different, and the phenotypical tree, I mean, you see blue and green are more closely related than green is to red, or, I mean, it didn't work out at all. He says, oh, I said, but just one tooth, come on. I mean, probably nutrition is more, and indeed, I mean, when Doug said, of course! I mean, what happens is that they are, the frugivores are together, the folivores are together, the insectivore is far from all the others. So he said, this is amazing, he said. You just have shown what biologists are taught is something that is out of fashion forever, namely form follows function. Well, we have not shown anything. What we've shown is that there was biological content in the results of this analysis, and so we are very encouraged by this. But as I said, it's not finished. We are now. In fact, I over the years, because we started about this, I mean, the paper, the PNAS paper, that was in 2011. It was probably written in 2010. Most of the research of it was done in 2008 and 9. So this has been a long haul. And since 2009, I have been regularly submitting proposals to NSF. I mean, the first proposal, I said, there's no way any of this can work. So we made it work, and we publish a PNAS, and then we write back a new proposal. We say, look, it works, and so on. And then they said, but what else are you going to do? I mean, you've already done what you were going to do, what you said you were going to do. So okay, so after we were turned down for the 5th time, I mean, I was very upset, and I thought, well, maybe it was a nice thing, but maybe somebody else will have to pick up the torch. Maybe I should. I mean, I'm over 60 now, I'm retired and so on. And then I got assigned to it. So now we're roaring to go because we have so many ideas, and we really want to use them. I mean, for one thing, Jeroen Lippmann and his students have found a way, if you have landmarks on surfaces, on many surfaces, to actually define a mapping on geometric basis in which you minimize conformal distortion. Of course, they do a discrete approximation, but for the whole collection jointly, and preserve all the landmarks. So when I heard this, I said, we have to try this on our teeth. So when I showed the mappings to Doug, he said, those are fantastic mappings. I mean, I expected that some of them would be great, and others he would say, oh, it's not quite right, that point, and so on. But I said, that's fantastic, then you can tell us what's wrong. We'll put an extra landmark there, and we'll get to maps that you consider are absolutely perfect. And if we have a large collection of perfect maps, then we can try to learn maps from that. If we learn maps, then maybe we can do automatic maps that way. And so that's what we're working on. It turns out that so far we have not found a single of these maps that are not perfect according to a biologist. I said, come on, I mean, it can't be that this is just conformal distortion taken as functional over the whole collection that biology minimizes. I mean, it must be more or something. What we were discussing this a couple of weeks ago, what we now feel is that by concentrating so much on these landmarks, and the landmarks themselves have biological significance for for the biologists, they actually don't see very much what might be wrong if the landmarks are right. They have, that's what they look for, and if those are right. So we need to find ways in which to check variability of these maps with respect to each other. And we are, we do have, so we're going to look at smaller collections and then a larger collection, see what changes when we do that. And so we are motivating that. But another thing that I am very, very much want to do, I mean, so they say they want only trivial anatomy. But that's okay if you think of lemurs or related primates. But if you're going to start comparing dolphins and chimpanzees, obviously there's not going to be a very natural, nice mapping that will work for such large things. So what I believe, but of course they don't expect such a fine-grained mapping. So what I expect we need to do is build the framework in a multi-resolution way, so that you have, at a very coarse level, you have, with very few characteristics, a very coarse approximation, with very coarse points on your base manifold, you have something with no element. But then you blossom open, and at the next level, you will have things with trivial element here, but it won't correspond very well to what's happening here, and so on. So I expect we will, that's how phylogeny will come in. And so But we have to build a mathematical framework for that. I mean, we defined these fiber bundle diffusions, which didn't exist before, but now we have to do this multi-solution thing. So there's a whole lot of math that will need to be built, and we're very, very excited.
Questions?
So, if you look at this tooth bundle and you see some non-trivial holonomy, or if
Yes.
you saw some curvature in this connection or something like this, what is there some sort of biological interpretation for what that means?
Well, for the moment, we're looking at things that are so closely related that they really shouldn't be. So, for the moment, what it means is that our maps are not good. I mean, that it's default of our maps. And so that's why we were looking at ways of more consistent, finding a consistent kind of average that would have no holonomy. And this method now that keeps all the landmarks the same. It's actually giving us very, and it is consistent by definition, not just on the landmarks, on everything, is a new step. But we do expect that there might be, I don't know, once we've built the right framework, that if we then look at things and attempt to map at a too fine level, that there might be biological significance in the way things don't work. But we don't know. For that we have to build it first. I mean, we had no idea that we would find this. I mean, once you find it, you have to validate it, of course. It's not because, you might say this is just a coincidence. But you use the tool and you find it, and then you can try to use it.
Yeah, it's evidence of something.
Yes.
You have to figure out what it represents, which
Yes.
is why you're doing this.
Yeah.
Other questions? Yeah.
My question could be silly. My question is about the resolution and its effect on reaching a conclusion. So this implies to, for example, when you place the landmarks, or even
Yes.
when you try to define your maps, you do need to take enough samples and so on and
Yes.
so forth. So,
Okay, our surfaces typically come at 30,000 vertices to begin, so they are kind of fine, given the structure. Computer graphics can work with much bigger measures than that. We downsample, we have exactly done that. We have looked at downsampling. We typically downsample to 5,000, and we have done a whole slew of experiments to find out what happens if you downsample more or less, and how that changes the error. And the error behaves exactly, you have an error that's proportional to a fraction of the average edge length. So you're exactly right. We have at every stage to validate what the error is of our method. And there are errors that can come in at many stages. There's the error in the CAT scan, and in the discretization of the CAT scan to the 30,000 vertices. And then we downsample, and so we are going to have an error proportional to our we then, although we do our maps, continuous maps, meaning we go to interior points of the triangles, we do expect, so that makes our error a little bit smaller there, but we do expect our error will still be comparable to a vertex, and we do indeed find an error on average of about half of an edge length. It's smaller in the edge length as we wished, but it's comparable. So yes, we have to do that in order to motivate, but what we find is real.
Can you give any warning to the biologists who try to use this method?
Any warning? Well, for the moment, only biologists who really talk to us on a weekly basis, we have weekly meetings, know enough about it to use it. So they have all the warnings. But we do want, and it's like with the D&E, to ultimately make packages. And actually, that's a big thing that Doug wanted. We want to make a software package, and Simon Grant has given me money to hire a programmer. To make packages that are user-friendly and, meaning probably not in mathematics. Biologists who know MATLAB are very thin on the ground. Who once it's in a user-friendly way of doing and that giving intermediate results nicely, Doug Boyer, so my collaborator, very much wants it to be accessible to people who are not trained morphologists. Because he says one of the problems with the present methods is that you have to have these years of training to do this reliably. And he says the results of these would be useful to many other people who have, from their own work, other things, I mean genetics and so on, and who might want to compare to morphology, but they don't have that morphological training. If we have software that will give them reliable results, that would be comparable to what a trained morphologist could do, that will make it much more powerful. And that was the initial goal. I mean, in the meantime, we have become more ambitious.
Well, I have a question about
Yes.
that. So you have these landmark points, which was sort of the starting point.
Yeah.
How do the trained morphologists know which points are landmark points? I mean, there must be something in the surface that they're seeing.
There is. There's no doubt there is. And some of the points are cusps and so on, but others are much more subtle. And it's hard for them to, if they could articulate precisely.
Right. Then you could encode that.
Exactly.
Right.
And they can. I mean, it's like with geologists. I mean, we could try to build an expert system like people do for geology, but that's not really what we're after. I mean, we want to get more insight into what's going on.
Other questions?
Yeah. How is this related to the applications of mapping the terrain? I mean that when terrain is mapped, people routinely fuse information obtained from different sensors, from different vantage points, in different illumination conditions. So this registration, it sometimes uses this landmarks. It's called feature-based registration. Sometimes it does not. So is it similar? Is it different?
It is in that sense similar that they try to define landmarks or SIFT or whatever, I mean points that they use as a register, as a reference in order to do that registration. But in all those applications, you're looking at the same object under different modalities. You use that it's the same thing you're looking at, but that you look at it from different modalities. We know that we're not looking at the same thing. You might say we're looking at some abstract truth expressed in different ways. But even then, we don't know the modality. I mean, so that makes it different.
Good. Well, let's thank Dr. Daubechies.